An international team of researchers from institutions such as the Emerging Technologies Research Center, Donostia International Physics Center, and Institute of Materials, is exploring the potential of van der Waals materials to overcome limitations in photonic integrated circuitry. Van der Waals materials, characterized by weak interlayer interactions, have garnered significant attention in recent years due to their unique properties and potential applications in photonics. Current photonic integrated circuits face significant challenges, including the difficulty in achieving high-quality optical interfaces, integrating multiple functionalities, and scaling down device dimensions while maintaining performance. The authors propose that van der Waals materials can provide a hidden advantage in addressing these limitations. The unique properties of van der Waals materials, such as their high optical quality, flexibility, and ease of integration with other materials, make them an attractive solution. By leveraging these properties, the authors aim to develop novel photonic integrated circuits that can overcome the current limitations in the field. The diverse backgrounds and expertise of the research team in materials science, photonics, and nanotechnology provide a strong foundation for exploring the potential of van der Waals materials in photonic integrated circuitry. The author's approach is built on the premise that van der Waals materials can enable the development of high-quality optical interfaces, facilitate the integration of multiple functionalities, and allow for the scaling down of device dimensions while maintaining performance. This approach has the potential to overcome the current limitations in photonic integrated circuitry and pave the way for the development of novel photonic devices and systems. The authors investigate the optical response of transition metal dichalcogenides, specifically WS2, in integrated nanophotonics, leveraging its high stability and optical bandgap. Ellipsometric measurements determine the optical constants of WS2, yielding etalon optical constants that agree well with theoretical WS2 dielectric tensors. The results reveal that WS2 exhibits giant optical anisotropy and a high refractive index, similar to most 2. Planar waveguide modes are recorded in WS2 flakes using a scattering-type scanning near-field optical microscope, confirming the observations. Fourier mode analysis reveals a fundamental mode whose dispersion perfectly fits transfer matrix calculations, validating the dielectric function. The refractive index and optical bandgap of WS2 make it beneficial for all dielectric nanophotonics compared to classical highly refractive materials. In comparison to other layered materials, such as MOS2 and HBN, WS2 forms part of a next-generation optical platform. However, a spectral gap exists between 2 and 4 electron volts, where layered materials lack superior optical response. Figure 1 presents the anisotropic optical properties of WS2, including the dispersion of in- and out-of-plane components of refractive index and extinction coefficient, as well as the birefringence of WS2 compared to other well-known birefringent materials. The maximum in-plane refractive index of WS2 in the transparency window is compared to other established highly refractive materials. Additionally, amplitude and phase maps of a WS2 flake measured by SSNOM are shown, along with lined profiles of the fundamental mode. The measured dispersion of the planar waveguide mode is compared with the theoretically calculated dispersion using the transfer matrix framework, showcasing the accuracy of the approach. The researchers investigate the impact of anisotropy on integrated circuits, focusing on photonic integrated circuits, PICs, design. In dielectric waveguides, the electric field can permeate into surrounding space and cladding, leading to parasitic crosstalk, characterized by the crosstalk distance LCT. To avoid bit errors, LCT should significantly exceed the characteristic size of a PIC. The researchers evaluate the effective mode index of the fundamental mode NEF, crosstalk distance LCT, and mode area as a function of waveguide height, keeping the waveguide width at 500 nanometers and wavelength lambda at 1550 nanometers. Contrary to expectations, the parameters that maximize LCT do not minimize the mode area. Instead, both LCT and the mode area increase as the waveguide height increases from 120 to 300 nanometers. The electric field distribution in a single waveguide is examined to explain the observed behavior. The decrease in the evanescent field strength created by the left waveguide at the location of the right waveguide causes more than an order of magnitude increase in LCT. The effective mode index nef determines the imaginary wave vector of the evanescent field through kappa approximately equals 2 pi lambda square root nef squared n glass squared, resulting in faster decay of the evanescent tails of modes with a higher effective index. The mode area is less dependent on the evanescent field, resulting in a lack of correlation between the mode area and LCT. The field distribution in the fundamental waveguide mode and waveguide crosstalk is illustrated, demonstrating that almost half of the signal power crosses over to the right waveguide for a 120 nm high waveguide, while there is no observable crosstalk in 300 nm high waveguides. To optimize waveguide dimensions, LCT is evaluated as a function of the waveguide core dimensions. LCT reaches a maximum and then decreases with increasing width due to two opposing factors: the increase in the effective index and the decrease in the distance between the nearest points of waveguide cores. At a fixed width, LCT monotonically increases with increasing height, following the trend established earlier. The maximum LCT of 4.7 mm is achieved with a core width and height of 440 nm and 240 nm, respectively, which exceed the width and height where the minimum mode area is achieved. The investigation of waveguide characteristics is extended to examine the impact of optical anisotropy. By assuming an isotropic core material with a refractive index equal to the in-plane refractive index of WS2, the crosstalk distance is found to be only a few percent larger than that of the anisotropic core waveguide. This is attributed to the small change in the effective mode index, on the order of 10 to the power of 4, which is surprising given the giant optical anisotropy of WS2. The small y component of the fundamental mode electric field contributes to this minimal difference. However, this argument does not apply to higher order modes, leading to significantly different cutoff curves for anisotropic and isotropic core waveguides. As a result, optimized waveguide dimensions and crosstalk distances are smaller for the isotropic core, with a crosstalk distance of 1.5 mm compared to 4.7 mm for the anisotropic core. The influence of anisotropic WS2 layers was measured and verified using near-field microscopy, revealing a giant optical anisotropy and a higher in-plane refractive index compared to other materials with similar optical bandgaps. Theoretical demonstrations showcased the potential of these unique optical properties in achieving ultra-compact integration in photonic integrated circuits. The superior performance of layered materials can be attributed to two key factors: the high in-plane refractive index, resulting in an unusually high effective index for the fundamental waveguide mode, and the relatively low out-of-plane refractive index, which diminishes effective indices of higher-order modes. This leads to an increase in the cutoff waveguide core size for higher-order modes, maintaining the single-mode regime in waveguides with larger cross-sectional areas, and resulting in lower waveguide crosstalk and increased integration density. Near-field microscopy experiments confirmed the excellent wave-guiding characteristics of WS2 waveguides, perfectly agreeing with theoretical predictions. The results establish a firm ground for the application of layered materials in integrated photonics, highlighting optical anisotropy as a valuable tool for optical engineers. The study employed spectroscopic ellipsometry and scanning near-field optical microscopy techniques to measure the anisotropic dielectric tensor and wave-guiding characteristics of WS2 layers. Ellipsometric measurements were performed using an imaging spectroscopic ellipsometer, allowing for signal collection from a small spot with a size down to approximately 10 micrometers in a broad spectral range. Near-field measurements were conducted using a commercial SSNOM in the reflection mode with tape polarization, with noise suppression achieved using a pseudo-heterodyne interferometer at the third harmonic. The authors present a comprehensive taxonomy of edge computing architectures, categorizing them into three primary classes: cloud-centric, phog-centric, and edge-centric. These classifications are based on the distribution of computational resources, data processing, and latency requirements across the network. Cloud-centric architectures rely on cloud infrastructure for data processing, relying on high-capacity networks for data transfer. Phog-centric architectures, on the other hand, utilize fog nodes for data processing, situated closer to the edge devices, reducing latency and network congestion. Edge-centric architectures process data directly on edge devices, minimizing latency and ensuring real-time processing. The authors also discuss the role of micro-data centers, which serve as intermediate layers between edge devices and cloud infrastructure. These micro-data centers can be deployed at the edge, providing localized processing and storage capabilities. The paper highlights the significance of edge computing in IoT applications, where real-time processing and low latency are critical. The authors emphasize the need for a hybrid approach, combining the strengths of cloud, fog, and edge computing to create a robust and efficient architecture. The proposed taxonomy provides a framework for understanding the complex landscape of edge computing architectures, enabling researchers and practitioners to design and optimize systems tailored to specific use cases. Recent advancements in nanophotonics have led to significant breakthroughs in the application of two-dimensional materials and transition metal dichalcogenides in photonic devices. A comprehensive literature review of 42 relevant studies reveals the vast potential of these materials in enhancing the performance of photonic devices. Two-dimensional materials, such as graphene and hexagonal boron nitride, exhibit exceptional optical and electrical properties, making them ideal for integration into photonic devices. Transition metal dichalcogenides, including molybdenum disulfide and tungsten diselenide, have also garnered attention due to their unique optical and electronic properties. The reviewed studies demonstrate the successful application of these materials in various photonic devices, including optical modulators, photodetectors, and lasers. The authors highlight the importance of understanding the underlying physics and material properties that govern the behavior of these devices. Key findings include the achievement of high-speed optical modulation using graphene-based devices, the demonstration of high-sensitivity photodetection using transition metal dichalcogenide-based devices, and the realization of low-threshold lacing using two-dimensional material-based cavities. The reviewed studies also discuss the challenges and limitations associated with the integration of these materials into photonic devices, including issues related to material quality, scalability, and device fabrication. Future research directions are identified, including the exploration of new material combinations and the development of novel device architectures. The reviewed literature underscores the vast potential of two-dimensional materials and transition metal dichalcogenides in revolutionizing the field of nanophotonics. Further research is needed to overcome the existing challenges and to fully harness the potential of these materials in photonic devices. In the realm of computational materials science and condensed matter physics, 3 seminal papers have laid the groundwork for advancing the field. Firstly, Kress and Furthmuller's 1996 work demonstrated the efficiency of ab initio total energy calculations for metals and semiconductors using a planewave basis set. This pioneering study enabled the efficient computation of total energies and electronic structures of materials, establishing planewave basis sets as a cornerstone of density functional theory calculations. Building upon this foundation, Kharichkin and Kress's 2006 paper implemented and evaluated the frequency-dependent GW method within the projector-augmented wave framework. This work showcased the feasibility of using the GW approximation to calculate quasi-particle energies and band structures of materials, providing a more accurate description of electronic excitations. Furthermore, Kress and Joubert's 1999 paper introduced a novel approach for constructing pseudopotentials from ultrasoft pseudopotentials, enabling the accurate calculation of electronic structures and total energies of materials using a planewave basis set. This projector-augmented wave method has since become a vital tool in computational materials science and condensed matter physics. By citing these influential papers, the authors underscore their reliance on established methodologies and techniques, highlighting the significance of building upon existing knowledge to drive progress in the field.